same as the first problem. No? We are only these capacitance added, no? For the
right.
So we have because larger resistor we have to choose the resistor.
Well, and you get attenuation, right?
Yes, in fact, I did. So at the end we have to select a resistor.
To just bias this point, right? You need some way to bias this point here, and a resistor is probably the simplest.
Okay.
But there may be other ways to do that. Okay, I'll start. Good afternoon, welcome to 240. So, a couple of announcements first. Today there is no office hour. I have to leave early and catch a plane. If you have questions, then please just come after the lecture or send me email, and I will try to answer over the weekend or Monday. Okay, then a new homework is on the web, and somebody already pointed out that actually it's all bogus. So particularly in problem 2, I specify the W over L of the transistor as being 100 over 0.5. Why not? I also specify V star, I believe it's 250 millivolts. And then I specify GM 50 microsiemens. And of course, by now we are over-specified, right? If we also assume that we have the 240 process. So let me just drop this, and you, for once, can use sort of our design approach in reverse, right? That's not normally how we would design a circuit, right? That's maybe analyzing the circuit, which is what most courses do, right? And so you, of course, you can do this also. So it just turned out to be the easiest fix for the problem. Also, for homework number 1, the solution is on the web. Problem 1 in homework 2 is fairly straightforward, very similar to what you've done already, except that the gate of a common source stage is capacitively coupled. So this is the output, and this is the input. And don't forget that there is a capacitive voltage division here, so that will affect your result a little bit. Just use the equations again and sort of do the same thing. By now it should be very straightforward, probably. And then there is also, whenever we have such a situation, we of course need to provide a bias for this node. And there are a bunch of ways to do that, but one solution is to use a very large resistor. For example, the simplest would be to use a humongous resistor like this. That would provide a little bit of feedback, but not very much, right? Okay. So, other questions? All right. So we've started talking about noise, and in particular, we talked about models of noise for noise models for resistors, and also capacitors in the inductors. Basically, there's nothing, right? Then we looked at the MOS transistor, and today I want to start by just quickly also talking about the BJT. These still exist, and in some cases they're really helpful, right? And of course, used. If you can set the camera a little bit different, otherwise my hands are going to fall off. Thank you. So a bipolar transistor, see, I'm used to MOSFETs. A bipolar transistor has, of course, also a small signal model. I'm drawing only the low frequency small signal model. GMVBE, or pi, and then, of course, also an R out. That's the collector. Emitter. And the base. And that's VBE. Okay, so what we want to know is what the noise sources are. Well, a bipolar transistor is really two diodes, and so that kind of suggests what noise sources we should expect. One of them is here. That's IC square, and it's 2Q times IC times delta F. Okay. And then there is also a diode between the base and the emitter, and we're going to get more shot noise there, and that's IB squared, and its value is 2Q IB times delta F. They're also written on the handout, these equations. And then in bipolar transistors, very often, so actually, yeah, one thing I should say that this IB, of course, sort of corresponds to the gate leakage noise current of a MOSFET, and because presently, at least in MOSFETs, that contribution is still negligible. MOSFETs have an advantage there that this noise source just plain isn't present or is not really relevant, right? Whereas in bipolar transistors, it's very often relevant. And in fact, that there is, not this homework number 2, but in homework number 3, you're going to look at a comparison between MOS and bipolar, and you will see that in some cases, the MOS, and in some cases, the bipolar transistor has a big advantage. Okay. In bipolar transistors, often the base resistance, there's just extrinsic base resistance, and its noise contribution, probably most sensibly modeled by a noise voltage source, is significant. So that's VB square is 4KT times, that's just the resistance of tying into the base, right? And there are all sorts of fabrication tricks, poly emitters and so on, to make that small, times delta F. But base resistors in the hundreds of ohms or so sometimes, or at least older technology have that, and then that can be a problem, right? If you drive this from a 50 ohm source, well, then the source may have a lot less noise than this base resistor. Okay, and we'll see later that even if you do feedback and so on, you still get the noise. You don't get the attenuation, but you still get the noise. The bipolar transistors, just like MOSFETs, they also can suffer from flicker noise, and I specify here one way of how this is often modeled. Some kind of a fudge factor times the current in the base times delta F over F, right? Because it's 1 over F noise. Okay, so that's the noise model for a BJT. Okay, so getting back to MOS. And I'm not going to talk a whole lot about flicker noise yet. I mean, in practice, when you're designing circuits, flicker noise is kind of a little bit a special case, and it's certainly very different from thermal noise. First of all, because it really occurs only at very low frequency, right? If there is the sort of the total noise ID squared, and then the flicker noise, as it decreases with frequency, it may not matter. So if you have a system that has, let's say, a bandwidth of 1 gigahertz or so, why not, right? And flicker noise is somehow down here, in a 1 megahertz or less bandwidth. This little sliver here may just plain not matter, right? In fact, if I had drawn it to scale, you wouldn't see it, and you would say, well, of course it doesn't matter, right? So that's one thing. The flicker noise may just, or it may be just that our signal is up here, and this thing is going to be filtered away anyways, right? And so flicker noise doesn't matter. In nonlinear circuits, a little bit different, right? In an oscillator or so, sometimes the flicker noise can be upconverted to the carrier. So then It's important. The other thing that is special about flicker noise is that because it really occurs only in a particular frequency band, there are a number of tricks that have been invented that allow us to actually attenuate flicker noise or to the point where it becomes irrelevant. So very often when it comes to flicker noise, we'll have to decide first whether it's a problem anyways, and if it is a problem, whether we want to use one or another technique on how to deal with it. So, but one sort of vehicle or one figure of merit, if you want, that is helpful in determining whether flicker noise might be a problem in a particular application is the so-called 1/f noise corner. And at higher frequency, of course, thermal noise dominates, right? And at low frequency, low enough frequency, it's the flicker noise that dominates if we have a MOS, for example, a MOS transistor. And this frequency here, we call this the corner frequency, FCO. Okay. So now we would like to calculate this, and for that we simply set ID 1/f square equal to ID thermal square, right? And this here was 4 kBT times 2/3 or gamma times GM times delta F, and then on here we have a similar equation. Kf times ID, and I certainly know this one by heart, but I actually keep forgetting this one, over L square times Cox times delta F over F. And now when they are set equal, then by definition this F is now at the F corner frequency. So all we have to do is we have to solve for this F corner frequency, and the expression is also listed on the slide as well. Yeah, something, right? So that's the result for this corner frequency. For just if you can use more soon, please, thank you. Oh, that's also that of course could be different for a more complicated circuit where you have more noise sources. So you can calculate that in that case also. Well, I cooked up a couple of examples here. If I set V star 200 millivolts, well, why did I choose that? Well, because, as we said, that's kind of a reasonable V star, right? By the way, the corner frequency appears to be proportional to V star, so if you cut it in half, well, the corner apparently also goes down by a factor of 2. The channel length, according to this equation at least, appears to play an important role, so I picked 2 different channel lengths and ended up with sort of tens to hundreds of kilohertz, which is about typical. One of the biggest problems with flicker noise, I may have said that already, is that often it's just not characterized. Often it's difficult for you to get good characterization data. So with flicker noise is really a big issue, like you build this wonderful 20-bit oversampled, I don't know what, front end with with A to D converter and so on. Then a flicker noise, right? In this 1 kilohertz bandwidth, just a flicker noise, of course, is all the noise you get. In that case, you may have to fabricate devices and extract flicker noise for them also yourselves. Also, depending on where you read this, flicker noise supposedly also depends somewhat on biasing conditions. So if you use a high or small VGS, you may actually get different amounts of flicker noise. There are more complicated flicker noise models available than the one that we are using here, but as I already said, right, most of the time we don't have the one single parameter that we need for our simple model here, and so how are you going to get the much more complicated or much larger number of parameters for the more complicated model? So flicker noise is often somewhat of a pain, and one way to deal with it is like in 240. Most of the time we just say, well, in that case where it doesn't matter. Okay, so now we kind of know what noise comes out of the devices, but of course much more interesting is to figure out what is the noise that comes out of our circuits that we build. And we start with a here sort of a first example is, if we can use a little bit more zoom, okay, I now set up just for the time being still, just a single transistor. I want to know what is actually the noise current that comes out of this. Here I do this simply because our equations, of course, immediately specify what the noise current is, and then SPICE has a statement that's called dot noise. And you have to specify where, at what node you want to measure the noise. In many versions of SPICE, there is no dot noise that measures noise current. There is only one for voltage. So in this case, where we want to really know the noise current coming out of here, is it for you? Is it also? It's not sharp, the image. It's not in focus. Or is it with my eyes? Well, okay. So then we can use this trans resistance amplifier, the ideal model in SPICE side, to turn the current into a voltage and then use dot noise on that voltage. That's what I've done here. SPICE will complain if you don't also add other elements to this node. So I just added a dummy resistor. Of course, this resistor here also has noise. Doesn't matter in this case because it's driven by a voltage source, and consequently its noise source is shorted out. Sometimes you do have a need in SPICE, hopefully only, for a noiseless resistor, and there is a trick to make those. SPICE has a GM element, G, right? And of course you can set it in feedback on itself, or basically diode connected transconductor, right? And interestingly enough, then those G, these synthesized resistors out of transconductors in SPICE, they don't exhibit noise, whereas the real resistors usually do, and in some more advanced version of SPICE there is a way to turn them off. Anyways, so I ran a bunch of simulations here, and the noise corner changes as a function of this. Basically, if I increase the size, and if you mill through the equations, you can see that also. If you increase the size of the transistor, the gate area, then the noise corner frequency shifts down. And the idea, sort of the physical explanation for that is that because flicker noise is a function of trapping, the larger a gate I have, the more I average out the effects of charge trapping, and consequently I get relatively much larger current, but less flicker noise. Okay. So again, very often we really want to know what is the noise, how is the noise affected on our circuits. And one question to ask is simply, well, how much noise comes out the other end at the output of our circuit? And so how do we calculate this? And I put purposely sort of the method on how to do that here, almost like a computer program. It's not very difficult. You know all the bits and pieces to do it, but it is really tedious. And so so often, if I've seen that you get to something trivial like a common source amplifier, and you just can't believe that it takes almost an afternoon to do a full noise analysis on that thing. Well, it's true, it does, right? At least the first time. Right? So it's really tedious, and I write this down so that if in case you have doubts on how can I get the noise, well, this is the recipe, and yes, it is really ridiculously tedious. So now let's apply this to something. The first thing is going to be, of course, we need a circuit, and then really immediately thereafter, we're going to use a small signal model. All of our noise analysis here is done in a small signal domain. I don't know how to do it in a large signal case. Okay, so here is our example. The example really is over here. That's really the example. it's a common source stage, resistively loaded, and also a load capacitor, small load capacitor. And then I want to know what is the noise at the output here, so I use a dot noise statement, right? And this is driven not just by a voltage source hooked up to the gate, but instead by a current source in parallel with a finite output impedance. And then also there is a capacitance, the parasitic capacitance of this current source. A sample application of this thing is a fiber optic receiver, where this really here is a model for the PIN diode that converts photons to electrons, and here the electrons come out and they are amplified here and give us a voltage. Right? So it's kind of a practical example. This part here is simply for biasing. Right? We've seen this already, that when we have a common source stage, we cannot just set the gate or the input voltage to 0 DC-wise, because then the transistor would be off and GM would be near zero, and it wouldn't work very well. So we have to set this to just the right voltage. And there are lots of ways to do that. One of them is to just run a .DC analysis and figure out exactly when the output is sort of mid-rail, and write down that output voltage to many digits. A simpler way that also is insensitive to variations in the process is to build some kind of a replica circuit that constructs the right biasing voltage, and that's what I've done here. This circuit here, if you compare, is really exactly the same, but I have set it into a unity gain feedback such that the output, such that it computes, this feedback circuit here computes the voltage that's required on the gate, so that the output voltage is equal to 2 volts. Right? Of course, in SPICE, it's trivial to do this. This is purely for biasing. We're not going to build this. It's just so that I can run my simulations efficiently and without worrying what the heck this voltage I need to put there. This circuit, of course, also produces noise, and I have not found a way to turn this transistor, for example, into a noiseless source. So, to eliminate the contribution from that noise that would then, of course, taint my simulation, I put a very narrow band low-pass filter here in the middle. Okay. So this thing here is really just SPICE tricks. You can invent your own. There are lots of ways to do that. This is the circuit that we want to analyze. Okay, so I mentioned that the number one thing is small signal model. And so we have our current source, or our input current source, IS, that has a finite output impedance, RS. It has a it has a capacitance, CS, and then that is applied to our MOS transistor, where it produces a VGS on its gate. Then we have the transconductor GM, VGS. Then at the output, we are going to have the RL. And then we also have CL here. And that's V out. Okay. All right. So now, of course, the transistor itself also has its own elements, like it has a CGS that is going to add to a CS here, and it has an R out that goes in parallel with RL. I kind of cooked this example that you can verify that those contributions are kind of negligible. The CGS is very small compared to CS, which I've deliberately chosen large at about 1 picofarad. And again, let's assume that our out was large enough that the 10K load here doesn't matter. So still the model will be just enough work to calculate the noise from this thing. So then there is the noise sources. So first we have here a resistor here that contributes noise IS square at 4 kT or S times delta F. Then here we have two noise sources, ID square 4 kT 2/3 GM times delta F plus, did I say RS? It's 1/RS, right? Plus I or L 4 kT 1/RL times delta F. Okay, so these are our noise sources. So we have here really three noise generators, and we want to know what is the total noise voltage VO of F squared that appears at the output of the circuit and is superimposed on our signal, right? Okay, so if we go back to our computer program here, then what this really says is that that we should set first all inputs to 0, and the reason really is convenience. And when we are dealing with noise, so that we have one problem on our hands, so that we don't want to deal with all our other problems at the same time, and really because we are performing our noise analysis on the small signal circuit, everything's linear, and so linear superposition applies. So if we want to later figure out what is actually the output of our circuit with a real input also applied, well, we just add the two results together, right? The two contributions together. So we set when we do noise analysis, we set all inputs to 0. Then we have to pick an output. Heck, we need to know what we want to calculate. We did that already, the output here. And then now it gets tedious. For every noise source, that could be a voltage or it could be a current noise source, we have to calculate now the transfer function from that noise source to that output. So, for example, for this guy here, we have to calculate what is H, let's call it H IS of S is equal to V out of S over IS of S, right? We have to calculate this, and then we have to do some more things about it, and later we are going to do the same thing also for this noise current source. Here we're lucky that we have two noise current sources that just add together, so we calculate the transfer function only once. So now calculating these transfer functions, of course, is nothing difficult whatsoever. It's just tedious, right? So this HIS is first we turn IS here into a voltage, and the proportionality constant for that is RS. Then we amplify it here by GM times RL, and if you want to be precise, then there is also a minus sign, although here we ultimately get rid of it. And then at higher frequency, of course, this noise current source experiences filtering. First, it experiences a pole produced by RS and CS. Then, in principle, also, of course, it has a coupling capacitance here, right? The CGD, and then here it sees another pole. Now, if this one here is not very small and we can't use the Miller approximation and so on, then this is a big error. And once again, I've cooked the example that this capacitance is relatively small compared to the 1 picofarad we have over here, and the gain from here to here, we've also made it, the gain is only 10, so we can even ignore the Miller effect. So in our case here, in this example, and of course not in every case, and not for every noise analysis, so we can ignore this guy. And so we have a system that really falls into two individual time constants times 1 over 1 plus S tau 1 times 1 over 1 plus S tau 2, with tau 1 is equal to Rs times Cs, and tau 2 is equal to RL times CL. So that now we can also calculate the pole frequencies. FP1 is equal to 1 over 2 pi tau 1, and that is equal to 160 kilohertz. Well, not too surprising, right? We have here a megohm and here a picofarad, so that gives a relatively low pole frequency. And then FP2, by the way, often the problem in how do we build a fast fiber optic receiver? Well, for good sensitivity, you want a big diode so that produces a large capacitance, and then the impedance here is fairly high also for a good diode, right? So and then this is about 600 megahertz. Probably a little bit questionable, right, whether we should even consider this anymore. I do it here because you will then see a more interesting plot we can try to interpret. Okay, so then what does our thing here say? Now we can calculate the noise at the output, so let's do that. So the noise at the output, VON, is a function of frequency, is now equal to, first of all, the noise source, so that we said that is 4kT times 1 over Rs times delta F times, and now the transfer function, HIS of S squared. Because here this is amp squared, we also need to square our transfer function. Very important, right? Before we've said that already noise powers add up, but not RMS values of noise sources. Right? Okay, and then of course we have also the noise from the other two noise sources, ID squared plus IRL squared times ID S squared. Right? And so this would, I guess, be RL times 1 over 1 plus S tau 2. Right? Okay. So this is really sort of ECS 105 or so, right? Analyzing small signal circuits. And the only difficulty is that it's just so many terms to take care of. It takes a lot of time. Boring. Okay, but well, I guess on the next slide you have a simulation of this. So now the top line here is the total noise that comes out of SPICE, and it looks like this. Let's try to understand. Well, let's try to understand this, and the best way to understand this is to go back to our equation that we had derived for the noise and look at every noise source independently. Okay? Let's look first at the noise that just comes from RL, because that's the simplest contribution, and that's this line here. So that, of course, is 4kT RL just at low frequency, and then at high frequency, FP2, it should start rolling off. FP2 was 600 megahertz, and 600 megahertz is here. Okay, so that seems to be a winner. And now, of course, we can calculate what is 4kBT times RL is 10k ohm, right? And take the square root, and I've done that, and I got something like 12 nanovolts per root hertz. And SPICE, not too surprisingly, agrees with that, right? Okay, so now now let's look at the transistor M1, and the noise from its current noise generator, and that's shown here. It holds off here. So apparently, actually, the transistor dominates noise at higher frequencies here, and then here it's something else that contributes. What is this thing here? What is this? Here, this is again 600 megahertz, right? We would expect that. But what is this thing here? It's a flicker noise, right? And so you actually can see flicker noise quite easily in this plot, because this thing here is actually produced by an RC filter, right? RLCL. But and so we get the standard 20 or n times 20 dB roll-off per decade. Here, this is flicker noise, and flicker noise goes with 1 over S. Power goes with 1 over S. So voltage actually goes with 1 over square root of S. So we get 10 dB per decade attenuation or slope. Right? Funny, but it helps. It's kind of a godsend, because we can see right away. Strange slope's got to be flicker noise, right? Now, if you want to synthesize flicker noise and you don't have it out of your transistor, then it's a little bit a question: how do you do that, right? Okay, but so at very low frequency, of course, the MOSFET again dominates, because it is the only flicker noise contributor in our model, at least, and its 1 over F noise corner is here somewhere 300 kilohertz or something like that, right? And then we have the third noise source, and that's I'm starting to run out of colors, and that's the source resistor, RS. So at low frequency, again, the same business as for RL. We can calculate, of course, what it is. And then we would expect here that at the 160 kilohertz, we'd expect this to roll off, and lo and behold, it does. And here it's absolutely the dominant noise source, and then it keeps rolling off, and of course here we're going to see a second pole, but it's no longer plotted on my graph. So it actually would go on like this. Right? It doesn't have flicker noise, the resistor. In principle, resistors can have flicker noise, but usually negligible, unless they're particularly bad. And so it goes flat here. So at very low frequency, then it's the transistor. Here it's the MOSFET that dominates. And then here we get the RS that dominates. And then here we get again the MOSFET to dominate our overall noise contribution. Okay. All right. So that's our first noise example. Now we basically know how to calculate noise, and we're going to do that many more times. So we can now ask the next question, that is, how should we represent noise in two ports? So the first way on how to do that, we've just talked about. We can figure out how much noise comes out the other end at the output of our circuit. And sometimes that is precisely what you want. Heck, the signal comes out there, the noise comes out there, and so that we can compare them. But sometimes that's also not very convenient. For example, it depends, of course, on the gain of the circuit. If you have a high gain amplifier, well, probably some of the amplifier's noise is also gained up, and we get more noise out of that amplifier. Is that now a worse amplifier than another amplifier that has lower gain and consequently also lower noise? Well, not necessarily, right? I mean, the signal is actually amplified also when the noise is amplified, and so it depends on the gain and so on. So sometimes it's very inconvenient, especially if you had an operational amplifier. It would be very inconvenient for the manufacturer to give you the noise at the output, because open loop, well, the gain is anyways extremely poorly defined. Closed loop with feedback, well, it's your business what feedback you put there. And how can he possibly know how much feedback you want to use? So in that case, the input equivalent spectral density is interesting. We're going to look at that next. Then we're going to look at a little bit at the signal-to-noise ratio. Noise figure is another very, very interesting measure that is related to signal-to-noise ratio that is used at high frequencies in high-frequency circuits. For example, if you have an LNA, a low-noise amplifier, in a radio, then usually it's specified by the noise figure. And the noise figure tells you that suppose that your input signal had a signal-to-noise ratio of 20 dB, and your LNA has a noise figure of 2.5 dB. Once the signal comes out the other end of the LNA, the signal-to-noise ratio has dropped from 20 to 20 minus 2.5 or 17.5 dB. And then you go into the mixer, and it also has a noise figure, 5 dB and so on, right? And ultimately, you can determine whether, once you come out the other end of your receive channel, you actually still have a sufficient or positive signal-to-noise ratio. So that's another figure. It's not used, we cannot use it in mixed signal circuits because it requires terminated terminals. And then the one that is, for us, is most important is sampling noise or cation C noise, so we're going to spend quite a bit of time on that one. Okay, so let's first get onto this input equivalent noise. Well, and I sort of listed buzzwords here, but let's go through that example. So let's say I have an amplifier that has some kind of an input. In fact, in our example, the input was IS, and then this was a common source amplifier that has noise sources built in, right? There was among a bunch of other stuff, and then somewhere it had an output, V out, and then noise was coming out the other end of this output, right? And it also has a transfer function, of course, that is V out over IS. Okay. Now, this is reality. Now, let's see how we want to model this. So here we're going to do the same thing again. Now we do as if this thing was noiseless. So we make a noiseless model of the amplifier. It behaves exactly the same thing as the real amplifier, but all the noise sources are turned off. Still has an output, V out. And now, of course, in order to make these equal, we introduce a fictitious noise source here at the input, IN, or II, EQ, equivalent input referred noise source, that models all the noise, and that's actually added by the real circuit. So it's a little bit deceptive, right? This noise source plain simply doesn't exist, right? It's just here for modeling. Instead of dealing with, in our case, 3 in a more complicated amplifier, maybe 100 or so individual noise sources, we say, we model all of these with one single noise source. Okay? And then, of course, the point is that this noise here is going to be amplified and appears at the output. Right? And in fact, the noise at the output in this circuit is, the H of S, of course, is exactly the same in these two cases. Right? I haven't changed my circuit in any other way. That's H of S squared, again, times IEQ squared. Right? So that's how much noise comes out of this circuit, given that so much noise I stick into it. Well, the thing is, now I want to make these equal. Right? So that this is a faithful model for the reality. And now it's a trivial thing, right? When I have a circuit, much like the common source amplifier in our previous example, I calculate what is the total noise at the output. And then based on that, it's a snap to calculate what the input referred equivalent noise source is, simply by dividing by the transfer function of the circuit. So IEQ is equal to V out noise that we know how to calculate, divided by H of S square, which of course we know how to calculate also. And you can of course do this also if the input is not a voltage source, but not a current source, but a voltage source, so you get an analog result. Okay, so the noise in our example VON square was approximately equal to 4 kT times 1 over Rs times delta F times H of S squared, and this H of S was Rs times AV0 GMRL times this 1 over 1 plus S tau 1, 1 over 1 plus S tau 2. Right? Okay. Now there were other noise sources, but we recall that the Rs was really the dominant one, so I'm not going to write that. Yeah. So what is IIEQ? Well, IIEQ square is simply equal to VON square over H of S square, and that is equal to 4 kT times 1 over Rs times delta F. Okay. So of course here totally trivial, right? Because the noise appears at the input, so so we just add it to the input there. If the noise source had been at the output or so of the circuit, then it wouldn't have been so obvious and trivial. Okay, so in SPICE it's also possible to tell SPICE, of course, to simulate this. And now something interesting happens. This is the input referred current noise source here, and I calculated that right. We of course can calculate this. It's about 130 nanovolts per root hertz, and that again just matches SPICE. Then a lower frequency here we have what's actually happening here? What's happening here? Why does the noise suddenly go up like this? Well, the reason is that this additional noise here is really noise from the transistor and RL. That noise, those noise sources, they contribute noise to the output of the circuit, even at very high frequency. But H of S, so the noise from these sources, let's say RL or ID, even at high frequencies, look something like this, right? And rolls off a little bit, but it rolls off at like 600 megahertz, right? But H of S rolls off at what did you say, at 160 kilohertz, right? And then again at 600 megahertz with the second pole. Well, if I divide this thing here, this noise, by this here, then starting here, because what I'm dividing by decreases, this thing must go up. So input referred noise, in general, at high frequency, if we have a physically correct model, a situation that actually could exist, at high frequency that always blows up. Right? It's totally normal. If it doesn't, and it's input referred noise, something isn't quite right. Now, most of the time, we are not actually really interested here anymore. Why not? Well, because this is beyond the 3 dB bandwidth of our amplifier, and no signals coming out anymore. If we are concerned up here, then the first thing we have to do is get a faster amplifier, and then we can worry about whether there is noise coming out. Okay. There is one more thing that I want to just point out, and there is also an example in the notes on that, and that is when we calculate input-referred noise, we have to be, even though we can't want to know the noise at the input of our circuit, we have to determine what is the output of the circuit. Most of the time that's not a problem, because most circuits, an op-amp has one output, right? And it's pretty clear what that is. But sometimes a circuit can have more than one output, like here, this could be used, this amplifier could be used as a degenerated common source amplifier or a source follower, right? And so we have these two different outputs. And when we calculate the input-referred noise, we have to calculate the output noise either here or there, and then divide by the respective transfer function. The results are not going to be the same. I'll let you do the calculation yourselves, but I just show the result here from a SPICE simulation. So this curve here, that's the common source amplifier, and this curve here, that's the source follower. And of course, I've chosen this example to show that, hey, it really makes a difference. So be careful about this. Okay. Okay. Now, there is one further little problem with input-referred noise sources, and that's is RS. Let's modify our common source example one more time, just a little bit. We have again RL, and now I make my RS here, and I drive it with a voltage source, VI. Okay. Okay. So H of S of this circuit is now minus GM times RL over 1 plus S times RS CGS. Let's assume that this was the only significant time constant in the entire circuit. So now I can calculate what the output noise is, VON. And now, see, this is the most common way on how to get astray and get wrong results with noise analysis. Now I'm not even going to draw the small signal model anymore. I'm not going to draw out all these individual noise sources, simply because it takes so much time. But I can promise you, I've drawn such models over and over, tons of them, probably thousands of them. Right? So maybe you don't want to jump too quickly, and sometimes draw it even if I don't. Okay, so ID square plus IRL square times GM times RL square, right, at the output. And then the noise from RS is V RS squared times H of S squared. Okay. Now, I could expand this a little bit further, but the point is that this thing here is a function of RS. Right? The amount of noise that we're getting from this amplifier depends on RS. And that's a problem, for example, with general purpose operation amplifiers. If you make an op-amp, you want to sell it, you have to specify how much noise it has, right? But you don't know what RS is, right? Whoever uses it will put whatever his situation demands, and so you would have to make an entire catalog of specifications for every possible RS, and obviously that wouldn't be very attractive. So the solution we specify VIEQ square for RS equals 0. And we also specify IIEQ square for RS infinite. Then afterwards, when we have an RS that is somewhere in the middle, we can combine these two results and get the correct noise at the output for a circuit, independent of the value of RS. Okay, I think I need to speed up. Huh? You have seen this before. Okay, so well, let me just sketch the concept. What we will split up the circuit really into. I usually call this case A, and this case B, and I calculate them separately. So in case A, I make RS equal to 0. So I have then, if my input I set that to 0, so I have VRS squared. RS is now 0, goes on to CL. Okay, and so then VIEQ square in this case is just equal to ID square plus IRL square over the gain of the circuit GM squared. And then I have case B. Now, so this is actually VIEQ square. Case B, there I make RS go to infinity, and now my circuit looks like this. VGS is now equal to IS times 1 over S times CGS. And V out over IS is equal to GM times that. GM times RL over S times CGS. And from that I can calculate IEQ square is equal to ID square plus IRL squared times S CGS over GM square. Okay. Now with these results, I'm all set and done if RS happens to be either 0 or infinite. In practice, of course, most of the time it's neither of these two, right? And but now I can calculate very easily the noise if I have a more general situation. So my model now is VIEQ square and IIEQ square CGS GMVGS RL V out So VON squared. Now the real noise at the output for the particular value of RS that I have here is VIEQ squared times, again, this GM RL over 1 plus, like the VIEQ, really, I can shift it over here, and then it's low pass filtered by RS and CGS. S times RS CGS squared plus ID squared plus IRL squared times just RL. No, I don't have these noise sources. My noise source now is IIEQ squared times the gain from here. Output, that's RS over 1 plus S RS CGS times then the gain of the circuit GM times RL squared. Okay. So that's the noise at the output, and I can simplify this a little bit. Approximately, well, it's actually, it's equal to ID squared plus or I squared. So now I use the expressions that I had calculated for IIEQ and VIEQ, plug those in and simplify times, oh what a mess, or L squared times 1 plus S actually the frequency dependence drops, so VO N squared. Okay. Now, if we go, I don't have the notes here anymore, but if you go and compare this to the analysis of the circuit that we had done before, without using this input equivalent noise sources, you will find that this result here is not exactly correct. And the reason is that when we use this representation, then all of the noise from the circuit is already modeled by VIEQ, and all of the noise is also modeled by IIEQ. They just enter the circuit in different ways as voltages and currents. Well, if there is any correlation between these two noise sources, then those contributions could add up and lead to incorrect result, overall result. And of course, generally the noise in VIEQ and IIEQ is correlated somewhat because it stems from exactly the same current sources, right? It's just a different representation of the same noise. And so in cases where when you do this calculation and you find that VIEQ and IIEQ contribute about comparably to the overall noise, then it is safer to just abandon this input referred noise sources and calculate the noise from first principles, right? Going to the output noise and calculating for the particular value of RS. But if you have an operation, if you're the manufacturer of an op-amp or so, then you don't have that opportunity. Sometimes they specify the correlation factors and so on, and then other ways to take care of them. Okay, so very closely related to input referred noise is the so-called MDS, so minimal detectable signal. Suppose that you have an operational amplifier that was spec'd in the data sheet as having an input referred noise voltage of 10 nanovolts per root hertz, for example, right? And you also hook this up to a sensor that puts out a voltage Vs. You know in your application that really, I mean, for example, this is a microphone, right? You know that ultimately this is followed by a low-pass filter. It's going to look at only the first 10 or 20 kilohertz of the signal. Right? In other cases, the bandwidth may be different, but you know what the bandwidth is. Then you know that the signal and the noise are going to travel through all this thing, and in the end, they're going to be amplified by the same factor because they go through the same amplifiers. In the end, you're going to left with the portion of the noise and the portion of the signal that falls into that bandwidth. Let's call this bandwidth B. Right? Then we know right away that the total noise, Vi total, is equal to 10 nanovolts per root hertz squared times B. Right? Or that is equal to, let's say B was 1 megahertz, a high frequency microphone or a high bandwidth microphone. And then this of course would turn into 1000 10 microvolts. Well, now it's just microvolts. The square root of hertz goes away, squared, right? So now we can compare this to Vs. And Vs, if Vs is less than 10 microvolts, well, it's going to be buried in the noise. So the minimum detectable signal, the minimum signal that we need to have here so that we have a signal-to-noise ratio of 1 or 0 dB is equal to 10 microvolts in this case. Right? So that's a very quick way, right? You don't really need to know a whole lot about what's happening here except for the bandwidth. It's a very quick way to figure out whether with this amplifier you have any chance of even detecting the signal that you want to know. Of course, it could be that there are further noise sources here that further corrupt the signal, and then it's even worse. But if here already you're below the minimum detectable signal, it's not going to work, right? There is no such thing that somehow makes negative noise, something like that. Forget it, right? Okay, so now we get to this concept of sampling noise. So nothing new. It's still noise. It's just yet another way to look at noise. And the way we are looking at noise here is a little bit different from before. Suppose that we had some kind of a system, a bunch of amplifiers, maybe a microphone or whatever, driving them and so on. And out of that comes a signal, an analog waveform, and also noise superimposed on that signal. Now, instead of looking at bandwidths and looking at this fuzzy stuff on an oscilloscope, let's assume that this goes into an A to D converter. Well, the ADC, in order to grab the signal, it runs on a clock, right? And so with the frequency of that clock, let's say 1 megahertz, so every microsecond it goes and closes a switch, quickly looks at the signal, and at the end of the microsecond it opens the switch again, and then it has captured the value and it converts it. Now, if you had 1 volt here, then it would capture 1 volt there, and it would then convert that 1 volt and give a digital representation. The question is, what happens to the noise? The noise is now no longer a signal that changes all the time. Once we've grabbed the sample, we've also grabbed the sample of noise. The noise, if we did that, even if, let's say here we put in a 0, right? Then we would be grabbing a noise sample. Maybe once we would be getting 1 microvolt, next time minus 2 microvolts, then 0.5 micro, whatever, right? We'd get random noise samples or so. What are they going to be, or what is their variance going to be, right? Because ultimately now, this is what we want to know. We don't want to know what is the spectral, what is the noise density or so coming out of this thing. We want to know how big these noise samples are, so we can compare them to an LSB, for example, right? If for the LSB of our A to D converter, let's say, is 5 millivolts, and our noise samples are 10 millivolts variance well, we know we've got a problem. Our A to D converter, it converts a signal, and it also converts a whole bunch of noise. Okay, so we have to calculate what the variance of this sampled noise is. So, so now the model we are going to take for this that is very applicable to many circuits. Instead of having just a switch here, we also have a capacitor. Right? The A to D converter, when it wants to look at the signal, it closes this switch, and then when it's done, it just opens the switch, and it keeps the signal and the noise on this capacitor and then converts it. Okay. So if we can figure out what is the noise on this capacitor, we know what noise the A to D converter converts. Now, what's the switch? Well, in the off state, it presumably is infinitely large resistance. In the on state, it's just a resistor. Right? Most of the time, these switches are made out of MOS transistors. They operate in the diode region where they use the switches. So they're really a resistor. So the situation we really have is a capacitor, and there is a resistor here. And of course, the resistor has noise, and we know what the noise of the resistor is. This is a reasonable MOSFET. It's going to be 4 KTR times delta F, right? So that's the noise here. So while the switch is closed, actually what's happening is that the noise VON of S over delta F, that's the noise appearing here, is going to be the noise that appears there, right? 4 KTR divided by delta F. And then that noise is going to be filtered by this low-pass filter that has a time constant, let's say here, right? The 3V frequency. And consequently, the noise at the output of this system, the noise that appears here while the switch is closed, is going to have a noise density that looks like this. It's simply the noise from the resistor filtered by itself and the load capacitance. Okay? But then, when we open the switch, what happens to all this noise? Right? All this noise that is distributed over frequency, it suddenly becomes one number. What is that number? Or, because we are dealing with noise, what is the variance of this number? Right? Well, you probably in signal processing courses have heard about the aliasing. Right? When we sample a signal, then the spectrum up to half the sampling frequency is preserved, and everything that's above it, above that frequency, let's say that right, this switch really runs at the frequency Fs. So up to a frequency of Fs over 2, we really keep everything around the way. Right? And then everything that is beyond, in some contorted flipping way and so on, is just boing, falling into here. So what's the total power of the noise coming out of these things? Once we open the switch, well, it's just the entire noise power integrated from 0 to infinity. Right? Okay. So that's what I've done on the next slide. I have here the noise of the resistor. It's filtered by, if you can use more zoom. Thanks. It's filtered by this RC low-pass filter, square again. And then the total noise that comes, so this is the spectrum of the noise. Now the total noise is simply this thing integrated from 0 to infinity. One thing that, if I haven't said it, not already, then I say it now. Noise spectra, for historical reasons, they're always taken as single-sided spectra. So the 4 KTR equation assumes that the noise is 0 for negative frequencies and is all at positive frequencies. So that's why we have this 0 there. Whatever. You can change all the books and put 2 KTR and then you integrate from minus infinity plus infinity. Okay. Now this integral is a little bit ugly, so on, but I figured out how to do that, and I got KT on C. Now you may have heard this already, but So I make this quick, but one thing that is very remarkable in this thing is that, yeah, I mean the noise comes from the resistor, right? But it doesn't matter what R is, it matters what C is. If we want to have little noise, apparently we got to make C big, right? Or, doesn't matter. In fact, we can see sort of why this is. Here I have two cases, two circuits, both cases 1 picofarad, but in one case I have 1 k ohm, in the other case I have 100 k ohm. And so I then, using SPICE, I plot the noise density that appears across the capacitor. So for the 1 k ohm resistor, of course, I get less noise. I have 4 nanovolts at low frequencies, but then the noise stretches out to fairly high frequency because I have a low resistor. I get a fast time constant, high frequency pole. The higher valued resistor produces a lot more noise, 10 times more noise voltage, right, at low frequency. But then because it's a higher resistor, it starts rolling off sooner. And the area and the integrals are the area under these two curves. That's what you're computing. And the area under these two curves, well, you can't judge it here because it's a log-log plot, right? It's always, we make always that error. But anyways, apparently, our integral tells us, math tells us the area is the same. Right? So when I run this with SPICE, then I usually use the post-processor to simply integrate the noise as a function of frequency. So that these are these noise integrals. The noise for the 100K resistor raises much more quickly, but then it just settles out more quickly also than the one. So this must be the 1K, and this must be the 100K resistor. Right? And in both cases, they settle to kT over C, 1 picofarad. And kT over C for 1 picofarad at room temperature is 64 microvolts, and that's another number that I know, RMS, of course. Right? So apparently, if we have a 1 picofarad capacitor there, we get noise samples of 64 microvolts. And it's totally irrelevant what the source resistance is. And if we wanted to cut this down by a factor of 2, if instead of 64 microvolt noise samples, RMS, we would like to have only 32 microvolt noise samples, how would we change C? Yeah? I got you. You have to cut C by a factor of 4, and the reason is that the n square is kT on C, but here we plot the density in volts per root hertz, so just volts. Right? This has units volt squared. Okay. So we took the square root of this, and consequently, if this I want to get down by a factor of 2, I need to get the square of it down by a factor of 4. Okay? Get a bigger C. Get a bigger C. 4 times bigger C. 4 picofarads we would need. Yeah. Yeah. So this is one place where C really helps. Huh? You're going to use a lot of C, and obviously, right, if you want to have really good, then your entire chip is just a big capacitor. Okay, now we can relate that also to noise bandwidth, right? Well, you can look at this yourself. So one of the troubles in these calculations, when we do those, is that we always end up with integrals, right? And this is an integral that we've seen just before. And here is a bunch of other ones that we also see sometimes in these noise calculations. Of course, sometimes you see yet another one, and then maybe you're able to reduce it to one of these forms, or you will have to integrate yourselves. But I found that I usually get by with these, and so I stick them in the course in the hope that you also will find them useful. So then, of course, after this, I immediately went back to our common source example, and now I calculate what is the total noise that comes out of this common source amplifier. I say now, at the output of my common source amplifier there, I put the switch and the A to D converter and so on. So this is the CL is actually part of the A to D converter. That's the capacitor that the A to D uses to hold the signal, right? So now it's exactly the same noise calculation I had before, except that now I have to integrate that noise from 0 to infinity, and in a little bit verbose way, I've put the result here. So this is the noise spectral density at the output that we had calculated before. Here, there's not. I put 2/3 for gamma, and here is the transfer function. Then we have to integrate this over all frequencies. This part here is independent of frequency, so I can pull it out, and the RL also. And then I get this integral here. I go to this table and find that, lo and behold, this integral looks just about the same as this one. If I make omega 0 equal to 1 over RLCL, and substitute and so on, and simplify this a few more times, and the result is, I mean, that again is remarkable. VOT square is, I have now a circuit that, well, okay, it's not very complicated, but it's a little bit more complicated, right? And the result again is kT on C times a factor, and I usually call this factor the noise factor, right? Sort of the noise penalty, right? Apparently, if I just use a switch and the capacitor, I just get kT on C. If I add an entire amplifier to the picture and other stuff, then that also produces noise. Then the end result is still going to be kT on C times some factor, a penalty factor for having put additional junk there. Whenever, that's actually sort of, doesn't always work that way, but it's not somewhat true. Whenever you add a transistor or other element to your circuit, you also add a noise source. And so the amplifier, not too surprising, added noise. Now the total noise that we get at the output is the noise just from the sample and hold plus additional noise due to the amplifier that apparently depends on the gain. Makes sense. I mean, if I have high gain, my signal is going to be big, but then the noise, unfortunately, is also going to be bigger. And the only way, really, to cut down the noise, aside from maybe using an amplifier that made this